The first lecture begins with the fundamentals. The good news is that the fundamentals are no different than in other courses. There are very few principles of physics that underpin everything that you acquire here as students. And you'll recognize these things. One is the principle of mass conservation, which in this course will go by the symbol lowercase m. The second principle is the so-called F equals ma. The proper name for that is the conservation of momentum. Momentum doesn't mean an instant on the time clock. Momentum, a moment. Momentum means movement. Science came in language in Western Europe, came from Italian, movimento, which means movement. And then the French who brought French into English during the Norman conquest, they say mouvement for movement. And that became moment in English. The force that is in the same relationship is proportional to the increase in the speed, which is called acceleration. It's all about movement, and is the stuff that is visible, where's the turning shaft over here. So the conservation of movement. So momentum conservation. The third principle is the first law of thermodynamics, also known as energy conservation. And there's another principle called the second law of thermodynamics, which belongs in another course. It's about irreversibility or one-way flow. A reality that's taken into account here in this sketch that came from my mental viewing, except that I have a special course for this called the sister course of this one called AME 531 Advanced Thermodynamics. Which I'll be teaching here next fall. So fall 2025. So these are the principles. Each comes with, meaning analytically, from these founders, I mentioned Fourier and others, with one equation, with one equality or balance or statement of conservation. You see, at this stage, I have to be, open and come to terms to tell you that this course is not about applied mathematics. I will show you the so-called governing equations. It's important to know them. They are all listed profusely in the textbook, and they are used. But what I teach is something like simply called scale analysis, which is the art of anticipating the result on the back of an envelope, because you have a very good feeling for the physics behind or underpinning the actual flow. Keyword flow. It means not only fluid flow, it means obviously the flow of energy. It means the flow of people, say, on the streetcars in the city. All of that is physics that respects these principles. And something else. The equations that are listed under these labels in the textbook refer to most general situations of flow, flow that carries stuff from here to here. And that means, if you can imagine, here's a space in X, Y, and Z. And in this space, which is three-dimensional, a thing, a body, or a smaller body. I stay away from the word particle because particle means that there's a bigger body that has billions and billions of these dots. No, I'm not teaching reductionism because everybody else around this building teaches that. I'm teaching macroscopic stuff that you can touch and grab and put in your pocket. So anyway, this thing has a velocity component called u in x direction, v in y direction, and w in the z direction. And this thing, whatever it is, an amount of kilograms or joules or some other measure of inventory, is a function of time in general. So the equations that are listed in the book are for the most general situation, which is three-dimensional, time-dependent. Those are the equations. But the examples that will populate the blackboard are, even though they are mathematically correct and derived from those equations, are for much, much simpler settings of one-dimensional or two-dimensional and time-independent, also known as steady state. You see? So I'm going to start only the beginning, the path of deriving these equations to show you how it is done, and then I will simply write on the blackboard the remaining equations. The simplest to derive is mass conservation. The other ones become progressively more hairy and repulsive for that matter, but useful at the very end. And every single one has a story, a bit of history behind it. And I will allude to that because the people who came up with these things deserve our admiration. Okay, so mass conservation. I assume all of you have taken undergraduate thermodynamics. Who has not taken undergraduate thermodynamics? Not everybody at the same time, please. Everybody knows thermodynamics? Well, I'm quite sure you don't know thermodynamics unless you took it from me. So make sure you take thermodynamics next fall. Okay. In thermodynamics, mass conservation is common sense. In thermodynamics, people talk about a region in space called system. Inside this box can be anything. The most important word in science is any. In other words, if you know something that's universally applicable, that thing is any. And, of course, let's call it box, black box in this case, has inventories. You can weigh it, you can whatever. And at this time, it has an inventory called capital M, a number of kilograms, where CV doesn't mean curriculum vitae, it means control volume. This box has a boundary, very much like the frontier around one of those countries, or maybe the barbed wire and watchtowers around the Gulag, you see. That's the square that I drew. Never heard of that? You're going to hear about that in this course because that is part of human reality. And in it flows stuff, mass, kilograms per second, called m dot in, or the flow may be in the other direction, out, m dot out. I drew only one inflow, one outflow, but you could have any number of these arrows piercing the barbed wire. Get it? And so what is mass conservation? It's, well, common sense. It's exactly what happens to your money in your checking account. The more you bring in, the bigger the inventory. The more you take out, the smaller. So the statement from thermodynamics is that the rate of change of this inventory, called mass, is equal to the sum of all the inflows minus the sum of all the outflows. You cannot have an argument about this. This is what everybody knows. It's not only about going to and from the bank, but you can think about everything else, you know, that is around you. Things that change in time, meaning inventories, vary in time because of these flows in and out. So, great. Let's find out the calculus representation, meaning, forget about calculus, the name for the technique is mathematical analysis. That's the name for the technique. The partial differential equation equivalent of this. In 2 dimensions, time dependent, looks like this. You have a 2 axes, x and y, and you have this control volume, except that the control volume is infinitesimal. So this is how infinitesimal calculus was invented. It was on the backbone of these problems that 200 years ago, names such as Fourier, Navier, Poisson, these are the big names, employed and developed, actually, and then employed. So you have a infinitesimal step in y, intersecting or conspiring with one in x. And that means that the control volume, this square, has the size delta x, delta y. So that is the size is delta x, delta y. And in it, oh, by the way, the inventory is so mass is the density of the material at this location times the volume. Get it? Coming in is a stream of size u. In fact, rho u is the horizontal component, and then the face, which is delta y. coming in from below is rho v, and then delta x. And the technique of infinitesimal calculus is to repeat yourself on this other face, which is a delta x step to the right, and write it the way you learn from these Taylor expansions as follows. You write it this way. Rho u plus partial of rho u dx times the step delta x. In other words, the original rho u, and then the tiny change in u having to do with stepping to the right, and then times the size of the face that's pierced by that flow, which is delta y. And then similarly, here you have rho v plus partial of rho v with respect to y, delta y, and then the face of extent delta x. And so I made a drawing of arrows coming in and leaving, which is equivalent, meaning it's the graphic equivalent of writing terms in these places. What I did not write is the left-hand side. And the left-hand side is obviously the partial derivative of this inventory of mass. So d rho d time, and then delta x, delta y. And then on the right-hand side, I would have to write 4 terms, 1 term for each arrow, except that I'm not dumb, okay? Because you see, this arrow is canceled by this term. And coming from below, this arrow is canceled by this term. And what is left are only 2 arrows that are leaving the box. So there is a minus this term, minus another term. I'll make it with a diamond. The second term that's subtracted is this one. So that's it. And then when you manipulate and you divide by this imagined small volume, you arrive at the mass conservation equation as a partial differential equation. So let's see what we get. Here's something else. All of you take notes by hand. You, by hand, take notes. Not computer. Computer does not help the brain. And do not watch movies here. Coming to lecture is not coming to the movies. Coming to lecture is not fun, okay? Every time I lecture, I remember my professors at MIT, they were so unconstipated. They were constantly slipping jokes into the program to keep the students awake and happy. All right. So what's left after you do these two operations? You get the mass conservation equation, partial of rho with respect to time, plus d dx of rho u, and then d dy of rho v equals 0. This is true at every point. In this general setting where the density is time-dependent, and not so general, the fact that you have 2 dimensions. If you are dealing with the situations as 3-dimensional, as I had sketched here, then by inspection, you add a third term, which is partial with respect to z of rho w, w being the velocity component in the other direction. Now listen, don't get worried. This is just the beginning. We will solve the so-called problems beginning with mass conservation in much simpler settings. Much simpler is will be 2-dimensional and then constant density, such as the density of a liquid, water flowing and convecting heat from here to there is a very common application. Even an ideal gas, such as air, when it does the heating or the cooling, that stream does not experience significant temperature excursions for the density to vary significantly. So in this limit, all of that reduces to du dx plus dv dy equals 0. So that is a carrot I throw in front of you for you to know that easier work lies ahead. But at this stage, I want to continue with the upper line to teach one bit of nomenclature. When you expand these terms, so you've got let's see, 1, 2, 3, 4, and then the last 3 give birth to 2 additional terms. So altogether, they form the following string. So the density, the time, plus u d rho dx plus v rho dy plus w d rho dz, and then the remaining 3 terms, which are all multiplied by rho, and inside you have du dx plus dv dy plus dw dz. All of that equals 0. In other words, I rewrote this version of the mass conservation equation. And now the nomenclature that I need to define, yes?
The row and then the parentheses, the stuff in the parentheses, I don't really understand. Like, what does that mean for like you to be changing the text?
Why all these terms proliferate?
Yeah. Like,
because I'm making 2 out of 1. From this one, I made rho du dx plus u d rho dx. So this one gave birth to this one and this one.
But like, what does that mean for like, if u, v, w is like the vectors, like what does that mean that change with x and y?
Yeah, you bring up vector. A vector means direction in the Latin, and that direction is represented by three velocity components. In other words, the vector, which I'll call very soon v vector, has the components u, v, and w. Okay? Let me do one thing, and maybe it will cover the answer that you seek. From a vectorial analysis, this thing is known as the, rho, and then times the divergence of that vector v. If you prefer that kind of notation, I don't use it, but that's how things fit into smaller and smaller lines, you see. And over here, this big deal is because you see the founders got tired of writing long equations. So they invented notation that represented this and represented that. So for this entire string, they wrote the so-called material derivative, material time derivative, capital D rho, capital D t, where the capital D over dt is a operator known as material derivative, which represents partial of with respect to t plus u partial with respect to x. And anyway, you see those things over here. It's very useful to see the front sausage written this way, because it all depends on on t according to this particular notation. And in this case, it refers to the density. So if the density is constant or not varying much, I'll show you what I mean, but not varying much. If the variation of density across this space is delta rho, but the actual value of density of the stuff inside the box is rho, meaning the thing we've been writing all over, say rho here, then nearly constant density is in the space where delta rho over rho is in an order of magnitude sense, not only less than 1, but smaller than at least 1 order of magnitude. So that means smaller than, say, 1/10. That's the idea, where the road to nirvana, which is this happy place where you can neglect the terms and you can accelerate your progress toward the solution. So when the density doesn't vary much, everything here is forgotten. This row, of course, will get canceled. And what's left is this equation, which in 2 dimensions has only 2 terms. So beginning with this moment, in this upper right-hand corner, I will accumulate the formulas that will become our, let's call them points of reference throughout the course. By the way, here's another thing to keep in mind. You've seen these formulas. So the course begins with the so-called fundamentals that are familiar to you. And in this course, you'll see why those fundamentals come together to open your minds to phenomena that are mostly invisible, but phenomena that have predictable behavior that is useful to you as people who predict how the device should be or how the device should function. And if you are even more curious, then you predict how naturally occurring devices function and are shaped the way that they are. Anyway, so mass conservation for us will be simply du dx plus dv dy equals 0.